Okay, let's move on to the next session. The next session is service-oriented architecture. We have one presentation in this section. The title is Signal to Service, Remote Control of Legacy Networks. The speaker is Brian Petersen from Ethernovia.
Thank you. Good morning, everyone. In this presentation, I'll be talking about the continued evolution from signal-oriented communications to service-oriented communications. Now, the term service-oriented is part of the SUM-IP name, but I won't be talking much about SUM-IP at all. Instead, I'll be talking about what things are like at the edges of the network, how establishing correct levels of abstraction is important for managing complexity, how positioning physical interfaces between these levels of abstraction can have a big impact on the overall behavior of a network, what a unified network might look like and what it might enable, and what might be possible if we take abstraction to its limits. So to a first order of approximation, it's all analog at the edges of the network. Every sensor or servo either provides or requires an analog signal. Now, simple things like mechanical switches are essentially binary, but we'll disregard those for the sake of this discussion. Let's consider, for example, an electric power steering unit. Its sensors include motor temperature, motor current, steering angle, and steering wheel torque. Its servo is, of course, the electric motor itself. I think we can all envision these as being analog functions. Now, we could, if we were so inclined, control this power steering unit directly from an ECU using these individual analog signals if we gave that ECU appropriate interfaces and strung a number of wires between the two. This is, of course, wildly impractical, and we wouldn't want to do this. And so instead, I'm going to take a brief detour into levels of abstraction. Levels of abstraction are how we manage complexity. An application that has to achieve some particular goal may take advantage of control algorithms. The application does not need to know the details of how those control algorithms work. It only needs to know how to use the interface to those algorithms. Similarly, a device driver has detailed knowledge of the workings of the device it is controlling, but it provides an abstracted interface to the control algorithms. So we have these levels of abstraction through a work our way up and down. Now, eventually, these numerical values have to be converted to analog signals, and that's what we see at the bottom. Now, if we were to position our physical interface, our electrical interface, further up in these levels of abstraction, we get something that looks like this. And now what we're doing is we're multiplexing those numerical values into the payload of a CAN packet. And by doing so, we've replaced that series of analog wires with a single pair of digital wires. Now, this is great, this is obvious, but this drawing is also rather misleading because in an actual vehicle, an ECU may have a dozen or more interfaces communicating with a wide variety of sensors and servos and other ECUs. And of course, CAN has been joined by LIN and MOST and FlexRay and I2C and A2B and of course, Ethernet. And so even though we've made progress by replacing analog wires with a digital wire, the ever-increasing proliferation of these various sensors, servos, and ECUs has not resulted in a reduction in complexity. All we've done is kicked the can down the road. Now, this drawing, which Chris shared yesterday, is not the product of my imagination. This is from an actual OEM vehicle that's in production today. And as you can see, there's a wide variety of network types, a lot of wires running in parallel, and a lot of wires running nearly the entire length of the vehicle. So the ideal and obvious thing to do is to multiplex those legacy networks over Ethernet. So this is not a groundbreaking idea. People that have worked with me know that pointing out the obvious is one of my greatest skills. So the important point here is that we can have a controlling ECU that is essentially the brains of the vehicle, and it is taking the advantage of the services of zonal ECUs. Those zonal ECUs provide aggregation for various signals and provide gateways to legacy networks. Now, with this approach, what we have is a controlling ECU that still is aware of CAN and the signals that CAN requires, but we've added tunneling capabilities to the controlling ECU. The zonal ECU serves as a gateway. So the CAN packet that is being conveyed via Ethernet is extracted by the zonal ECU and then transmitted on a CAN interface. Our CAN-based sensor servo at the edge of the network is operating in the same way it was before. It's sending and receiving CAN packets in the normal manner, and is completely unaware that its CAN packets were conveyed via Ethernet for a significant portion of its journey across the vehicle. Now, we have a lot of options when it comes to encapsulating these CAN packets. One option is 1722, where we can take the CAN header fields and map them to 1722 header fields. And then the CAN payload is conveyed as opaque data. Another option is to convey the entire CAN packet, the header and the payload, as opaque data. And we can do this over UDP, and we can add a sum-IP layer if we so choose. Now, while the details of these various encapsulation methods differ quite significantly, the underlying principle is the same. A CAN packet's receive interface and message ID values are used to determine the CAN packet's ultimate destination. And the destination information is used to craft a properly addressed encapsulating set of headers. And then the packet is sent off to the gateway where the CAN packet can be extracted. Now, you notice in this arrangement of headers that these are all unreliable connections. We've got Ethernet and UDP are both unreliable. But there is a place in networks, of course, for reliable connections. I think a strong argument can be made that the vast majority of in-vehicle communications is of a periodic nature. And with periodic data, if a packet goes missing, the best policy is generally to wait for the next packet. You don't attempt to retransmit a missing packet in this case. But there are uses for reliable connections, and they come in the form of things that resemble file transfers. So things like map data, software updates, things like that are file transfers, effectively. And file transfers do not generally have performance constraints, but they do have one significant constraint, which is they are intolerant of data loss. So if a packet goes missing, it must be retransmitted. And a protocol such as TCP is a very good choice for this. Now, I've laid the groundwork. What does a unified network look like? And if we had such a thing, how could we take advantage of that? And when I speak of unifying the network, what I'm speaking of is all of these colorful connections out of the edges of the network. And to unify the network, all of these connections must be Ethernet. Okay? I believe that this is our inevitable future. And the reason I believe this is that Ethernet has dominated every domain into which it has been introduced. Examples include enterprise, carrier networks, and data centers. And Ethernet was either the first network there and fended off competition, or it was invited in and supplanted existing legacy networks. I believe this will happen in automotive as well. Now, one of the reasons that Ethernet can be very effective in these various domains is its cost advantages. And with each speed grade of Ethernet that's been introduced over the years, it has followed a rather predictable cost reduction curve over time. And again, this will apply to automotive as well. And what this means is that the legacy automotive networks, a lot of which were motivated by their cost advantages, will not be immune from this competitive pressure. Because eventually, Ethernet will reach cost parity with CAN. Now, again, pointing out the obvious, the benefits of Ethernet, chief among these are the longer payloads and the higher bandwidths. So if we had Ethernet everywhere, how would we take advantage of this extra capacity? And my suggestion is that we add layers of abstraction. So here's a hypothetical CAN sensor out at the edge of the network that has to deliver a series of scalar values to a controlling ECU. A data transformer is used to take those scalar values and pack them carefully bit by bit into a CAN payload. On the receiving side of the network, a complementary data transformer extracts those bits and creates a C struct that is then usable by software. And these transformers can be implemented in dedicated hardware or in software. such as the AutoSAR Classic ComStack. Now, this is what that same set of scalars would look like if they were encoded using Google's protocol buffers. Every element of a struct in this protocol has a tag, and the tag contains two elements. There is a type indicator and an element identifier. The value itself is encoded such that the number of bytes required to convey the data across the network is a function of that value's magnitude. Effectively, all of the leading zeros are suppressed. Now, in the best case, this is going to take more data. And depending on the values you're conveying, it could be far more than the 12 bytes I've indicated. And this ignores the 50 or 60 additional bytes that are required for headers and Ethernet overhead. So you may be asking yourselves, okay, why would I want to increase the number of bits on the wire by an order of magnitude to convey the same amount of information? And the reason for this is by taking this step, we've dramatically simplified the overall network architecture and the complexity of the software. You notice our controlling ECU is no longer CAN or tunneling aware. And the zonal ECU is no longer a gateway, it's just a bridge. Now, you notice the software stack on the left-hand side for our sensor at the edge, its stack has gotten taller. The good news is that compute continues to get cheaper the same way networking gets cheaper. And if not today, soon, this compute will be cheap enough that having this kind of capability out at the edge will not be questioned. So once we've done this, once we have IP communications from the center all the way to the edge, and we've got the ability to serialize and deserialize structured data, we have all the building blocks necessary for remote procedure calls. A remote procedure call, in a nutshell, allows us to call a function that resides on a remote system, and we can supply structured data as a parameter and receive structured data as a result. And we're passing structured data instead of device-specific bit-packed signals. RPC is a widely adopted solution for scaling huge systems, and there are numerous protocols available from which we can choose. Just one example is Google's gRPC. Now let's imagine what's possible if we take abstraction to its limits. Perhaps USB points the way. All of these mice can be plugged into almost any computer, and at the very least, you can get the pointer to move and you can click on an item. The computer understands what a mouse is simply by recognizing how it's trying to communicate. And remember installing printer drivers? Those days are largely behind us. And the reason for this is Apple wanted to introduce printing to its iPad, and it did not want its customers installing printer drivers. And so they developed the AirPrint protocol. And what that did is it moved the burden of rasterization from the host computer to the printer itself. And as a scaling strategy, moving compute to the edges near where it's needed is a good way of scaling system performance and also managing complexity. The iPad and other systems that adopt the AirPrint protocol don't have to run printer drivers. They just have to adopt that protocol. And they can work with any printer that adopts the same protocol. So why not use the same model for sensors and servos and other elements at the edge of the network? With cheaper computing and cheaper communications, this should become possible. Why continue to burden the central ECUs with all of the complexity of having to maintain what are effectively device drivers? So I'm going to leave you with some questions to ponder. If we had Ethernet everywhere, how would we take advantage of it? If we had all of the elements and compute resources all the way to the edge of the network necessary to support remote procedure calls and the serialization of structured data, what could we do with that? What would that enable? And what if we had standardized class-specific APIs to allow these sensors and servos plug-and-play operation? You can imagine whole categories of common peripherals in a vehicle, whether it's a window regulator or a stereo or a headlight module that can belong to a class that adopts a standardized API. And if we had these APIs, then the technology and the algorithms that reside in these sensors and servos could be allowed to evolve separately from the software running in the controlling ECUs. And if we make these changes, I think we could unleash tremendous efficiencies. So now that I've posed some questions to you, I'm happy to take your questions.
Any questions?
Martin Miller, Microchip. You had on your protocol list some IP and 7022, but don't you think it would need both, because there is some kind of service which needs streaming data, for example, if you take LEDs or light applications, and then you have this kind of control applications where you more would you prefer some IP?
Agreed, and my intention was not to imply that those were exclusive of one another. They could be used in combination for various aspects of the overall problem. Thank you. Yes.
Hi,
Hi.
I'm Shui Shizuka at Toyota, and I have a question. Please let me show your CAN to Ethernet packing slides. You showed 3 methods, IEEE 1722 and simple UDP and some IP. Please could you show me that slide which shows CAN to Ethernet packing page? Yeah, that's right.
That one?
Ah.
Yes.
My question is, which one do you think the best solution for CAN to Ethernet conversion format? And you mentioned that last page, you recommended that gRPC would be the better solution. So you think that third one would be better, right?
Even though I'm a very opinionated person, I don't have a strong opinion on which one of these would be better. It depends on your overall system architecture that you're trying to put together. There are some simplicities associated with doing the packet processing for encapsulating the entire CAN message on top of UDP, because you don't have to map headers to new headers. You're just encapsulating, so that's a bit simpler. But these are all roughly equivalent in their capabilities for just conveying CAN packets. Now, bear in mind, what this slide represents is an interim solution. It's what we have to do today because we do have to support these legacy networks for a little while longer. Ultimately, these sorts of encapsulations won't be necessary because we'll be speaking Ethernet IP all the way to the edge.
Thank you.
Of course, thank you.
Abbas Halusha. You noted standardization as one of the topics towards the end. We have 10 base T1S, we have 100 megabit, 1000 base T1.
Could you speak into the microphone? I could say. Thank you.
They're all standard 10 base T1S, 100 base, 1 gig, multi-gig. What other standards that need to be in place to fully implement or start implementing?
Well, I'm not quite getting your question. What is?
One of the notes you made towards the end, maybe the last slide or the slide before it, standardization to implement this.
Let me skip ahead and see. This one here?
Yes.
Okay. Yeah, whenever referring to standardized, I'm not referring to the layer 2 protocols. What I'm referring to is APIs. So these would be the context and elements and requirements of the structured data passed via something like RPC. So that's what I'm referring more to software level APIs than I am to Ethernet at this point. Any kind of Ethernet-based transport would be adequate. The only thing that matters is cost and bandwidth. Yes.
I'm Kenji Nishikawa from TT Tech Japan. I think many of the control systems based on CAN network is designed to work under this CAN and some of the latencies which CAN delivers. And if you are transferring this to this CAN and from signal to service network, can you just transfer the system, or do you think you need to redesign the system? So if you limit these latencies, in certain range when you transfer it to the service network.
Okay, if I'm understanding your question, the CAN systems today have a certain latency characteristic.
Yep.
And the part of that may be due to their simplicity. And that if we move to something, what I'm suggesting, which has more layers, it would take longer to communicate. Is that your question?
Yeah.
Or how do we address that?
Yep.
Well, one potential solution, and again, this is my purview, I'm a chip designer, is put those protocols in hardware. Do that work in a dedicated piece of hardware instead of a processor. And then you can eliminate the latency problem.
Okay, thank you.
Okay, thank you.
Christoph Golub, BMW. So first of all, I fully understand where you are heading. Just what I not fully get yet is the pretty low bandwidth area where it's really just short signals, but far often. One example would be wheel ticks, where you get one tick every 3 centimeters a wheel moves. And now imagine it's a German problem, traveling 200 kilometers per hour. So you just get very little information, but really, really often. By putting this on Ethernet, every time you have very little information, but really, really often, you just add a header.
I understand the point you're making, and let me try to address that. One suggestion might be, and this is not my area of expertise, that never slows me down, is that you put more intelligence in that sensor. So it can go from here's a tick, and when it gets to a certain point where the ticks exceed a certain number of ticks per second, it's starting to say, now I'm seeing ticks at this frequency. So you start reporting frequencies instead. And so the rate at which you're reporting data caps out, because you don't need to know 10,000 times a second how fast the wheel's turning. You only need to know maybe 100 times a second how fast the wheel is turning. So that would be one alternative. Just put a little more intelligence out at the edge.
And the other question, probably coming from the same area, you said computing power is getting cheaper and cheaper. I fully agree, and I fully agree on QAM computing power. The rate computing power gets cheaper in ASIL, and especially in ASIL D, it's not the same. How do you see this? So here we are currently facing problems that our ASIL D controllers have problems doing a lot of Ethernet quick.
Okay, again, like the previous caller, sorry, not questioner, if we embed a certain amount of this processing in the hardware, instead of asking a little teeny tiny microprocessor to do the work, you can make it run really fast, it consume very little power, and that logic can be very small. And so just like we use GPUs and neural networks to do advanced processing to offload the processor, and that's the reason why our telephones' batteries last all day, is because they have these specialized processors. And the same thing applies to networking.
So something like putting the COM stack not in software, but at least pushing parts of it in hardware.
Exactly.
Thank you.
Of course, thank you. Any other questions?
We have a few minutes for question session. Any questions?
Yes.
Mark Fu from Active. So I saw you have a block diagram. You have a controlling ECU, you have a zonal ECU, and
Yes.
you have a CAN-based ECU. And my question is, I thought the zone, so your goal is you try to simplify the zonal ECU. So the zonal ECU only the gateway or routing, right?
Right.
So I thought that the software-defined network is another way around. The zonal ECU suppose have a more function. So suppose I think should get rid of the CAN, so it will become the edge nodes, direct connect to the ECU, the sensor, right?
Right. Logically, the centralized ECU that's doing the control of the vehicle would be speaking directly to the sensors at the edges.
Right.
Okay. The zonal ECU in my model would simply be a bridge. And you could have as many hops as needed to get out to the edge where that sensor lives.
But I thought the zonal ECU will upper integrate all the edge ECU to the zonal ECU. So in the ideal, the zonal controller, you don't suppose to have any edge nodes. It is the edge nodes, edge ECU, right? So the zonal ECU will link to the sensor through the entry ECU, like SPI, I2C. So there's no CAN or Ethernet anymore.
Right, but if I'm understanding your question, my intent is, in this suggestion, is that we're replacing everything with Ethernet. So all of the interfaces between ECUs, whether it's a simple sensor or a zonal ECU or a controlling ECU, everything is communicating via Ethernet. So all of the gateway functions can go away.
Okay, thank you.
Any questions? Okay. Oh, oops.
Yeah, please.
So my name is Thomas Königseder from Technical Engineering. So I totally agree with you because I was the one who was trying to bring Ethernet to the car. But what I do not agree with you is that Ethernet will be the only solution. Because in the car, there are very effective solutions already today, and there is no need to change them. You're totally right when you talk about the costs of microcontrollers and the performance that will go down. But you should look to the power dissipation that you will need, and you should look to the effectiveness of a solution.
Okay.
And today, they are very effective solution and would be very bad if we destroy them. Interfacing to this solution, I'm totally agree. But please be careful when you say everything will be done on Ethernet. Only as a comment from myself.
No, that's an excellent point. And if we have an existing solution whose cost and power characteristics and latency characteristics are highly optimized, there would have to, and let's say an Ethernet physical layer solution didn't quite measure up. It was some percentage worse than the existing solution. There would have to be some compelling reason to take that downgrade in efficiency that makes the Ethernet worthwhile.
Yeah, but I'll give you one example. For example, CAN. Yeah? CAN is a very good solution if you use it in a limited use case. Okay? CAN is a problem if you use it in a big car. But if you use it in a local cluster, you will have a very effectiveness, very, very high effectiveness, and this is good. And from my point of view, as soon as we can, let's say, having the networking and the gatewaying done right, you have a very perfect solution already today, well established, everything done. Why should we kill this type of solutions?
Okay, well, thank you.
Oh, thank you.
Any other questions? All right,
It's,
thank you.
it's just 10 o'clock, so
Thank you very much.
Thank you, Brian, for the great presentations.